Hey guys, so this video is just sort of a general overview on vectors. And to do that, we're actually going to start out with just some basic trig review. I drew this on the board, I think, for some of you guys, but some asked some follow-up questions about why we know that our angle is this inverse tangent for here. So I'm going to kind of show you guys why that's the case. So first, just let's remember just SOHCAHTOA essentially here. So sine is equal to opposite over hypotenuse, right? So cosine is equal to adjacent over hypotenuse, and then TOA, tangent, is equal to opposite over adjacent, right? So we could basically just look at that here and realize that, so when we say opposite, we mean like opposite the angle. So this just translates to sine of theta is equal to opposite, what is opposite? Y over the hypotenuse, right? Cosine of theta is equal to the adjacent side, so this is adjacent. So x over hypotenuse, and then tangent, right? Tangent of theta is equal to opposite. So opposite here over adjacent, so y over x. If you don't remember your SOHCAHTOA, definitely review that one. It's going to come back to bite you pretty hard. But from here we can also look at that and see that that's the case too. So I know that tangent, right, just from the trig identity, is equal to sine over cosine. If you don't believe me, you can look this one up as well. And what we have for sine and cosine, we have y over h, right, is equal to x over h, and that's going to turn into y over x, and we have 1 over h, right? So that's just going to become, this 1 over h is just going to go to 1. We have tangent of theta is equal to y over x. So we want to find the angle. So to find the angle, we have to take the inverse tangent of both sides. So we're going to end up with theta, right? Because tangent negative 1 of tangent of theta is equal to theta, right? And then on this side, we're going to end up with tangent negative 1 of y over x, right? And that's going to give us our final angle. To find your angle, you could also use any of these identities here. Like say you know x over h, you could do cosine to the negative 1, right, of x over h is equal to theta. You could do this in any number of ways just by using the trig identities to solve for your angle. Depends on the problem. I think that these few here will just be the most useful, but feel free to manipulate them in any way you need to solve the problem. I don't think you're going to have anything that's too trig intensive, but just some background about kind of like where that comes from. Okay, so why are we talking about trig, and why do we care about these algebra or trigonometry throwbacks here? Well, when we break up our vectors, we're basically using the same trig rules. So by that, I mean, okay, we have an angle, we have an angle here for our vector, right? And our vector is A. So just to note, do you see this little line on top? Line on top. Oops. Line on top. That means vector. Means vector. You might also see these like unit directional vectors. They have these little hats on top. You might have heard me call it x hat, y hat, or z hat. This also means a vector. These little hats are usually more common on unit vectors. So these are unit directional vectors. You can also find different types of unit vectors, and we'll talk about that a little bit later, but we're not going to cover it in this video. Okay, so there is a Cartesian representation, okay, which means that we have things in the x, y, and z direction. Then there is also something called a polar representation. And in the polar representation, you are just given an angle, or a magnitude here, right, and an angle. In the polar representation, when they give you an angle, what they mean is it's an angle that's coming off of the positive x-axis and rotating around. So if I am given a polar angle, this would be the positive direction. And then if I'm coming the other way around, this would be the negative direction. That might be a little bit confusing, so let me draw maybe an example here. If I'm given a negative polar angle, negative 35 degrees, I would start measuring from this direction. If I'm given a positive polar angle of, say, 181 degrees, this looks bigger than 1 degree, but you know what I mean. I'm going to go in this direction. So that's just how things are represented when we're dealing with them with polar coordinates. That doesn't necessarily translate to how we break up the vector itself. So when we're dealing with vector directions, we want to basically take our starting vector, right, and we want to break up the components into a right triangle so that we can use trig to find the magnitudes of the side if that's what the question asks for. So when we do that, we basically only need to find the angle within the right triangle that we're trying to find, and we use that to find our components. For example, a sine theta, or on this side, a cosine of theta, right? To find the length components on in the x and y direction, okay? So for those of you guys who are confused kind of with the fact that we have these angles that are larger than the actual angle that we're looking at to solve for these triangles here, that's the reason why. That's just because this is a traditional polar representation. So in some problems you might be given a magnitude and an angle and then asked to break it up into vector components, okay? So this is kind of what you're dealing with here. All right, so, all right. You may notice that these look very similar. So if I go up here, right, and I'm looking at my SOHCAHTOA, when I have so this AY, this means magnitude, right? So if I have AY vector, I'm going to need the magnitude in the y direction, and I'm also going to need a direction, okay? A vector is composed of two pieces. Essentially, we need the magnitude and the direction, okay? If we just have the magnitude, right, and not the direction, it's not a vector anymore. Magnitude can also be written with these two little pipe operators on the side, and that just would basically mean the length or how much of a quantity you have going in one direction. So a magnitude could be a force or a velocity or an acceleration. It's just basically how much of that thing is going in the direction that you're looking at, okay? So magnitude is just the value, whereas if I add a direction, right, so AY and then I have the y hat, that becomes a vector. Oops, sorry. The full vector itself is actually composed of both of these. So say if I have AX, I have the vector AX in the x hat. My A vector, which would be all of them, so it would be this, when I'm saying x, this x piece, right, this x piece here. So in this case we have positive x, because look at our coordinate system, this is the positive direction, this is the positive direction, positive x, right, and the positive y direction. So I would end up with AX, right, so AX x hat plus AY y hat is equal to, and then if we look at our sides here, just using trig, that's how we find our side lengths. So we have a cosine of theta in the x hat plus a sine of theta in the y hat, okay? That's how we break up our directions, okay? If you're not super comfortable with these, or if I kind of went over this pretty quickly, feel free to rewind back a little bit. Also, I encourage you to try some problems. I think there are some in the week 2 folder and also in the week 1 folder where you can calculate and find vectors on your own. You'll either be given a polar coordinates and then asked to convert them to Cartesian, or you'll be given Cartesian coordinates and asked to convert them to polar, okay? All right. And then you'll notice that finding the magnitude for A, which is just when we have remember, no vector sign, so it's just the magnitude, which is how much in a direction. So the magnitude for A is just sort of the length of this line here. Notice that this is just the Pythagorean theorem. So we have the magnitude in the x and the magnitude in the y, so how long in the x here, how long in the x, and how long in the y, okay? These two squared, so this little subscript means A in the x, so this AX, and this little subscript y in the y direction, okay? Again, so we have inverse tangent of y over x, should be very similar to what we did before. Okay, so feel free to go back to these problems and do a couple of examples if this isn't making sense for you right away, or you can go ahead and stick with me for this video and then go back afterwards, okay? So adding and subtracting vectors. So this part should be pretty straightforward. The notation tends to confuse people. So what this is saying here is I have some vector c that's going to be A added to B. So when I add my two vectors, I need to add all of the x components together and then all of the y components together. So say I have a vector A, and I have, so I have 1 in the x hat plus 2 in the y hat, Okay, so if I drew it, what that would look like would be 1, okay, and 2. So this would be like my x direction, and this would be my y. Oh, sorry, that's the other way around. This would be my y direction, and this would be my x direction. Okay, and then if I drew my vector, that's where it would be. Okay, so these are basically just coordinates, right? This would be like if I'm drawing a vector that's going to the point 1, 2. You may also see vectors represented like this. This is the same as this, okay? So if I have this vector, right, A, and then I have another vector B, B is equal to 2x hat plus 3y hat. Okay, now we need to add them together. So what that's going to look like, so let me ask myself, so what's my ax component? Well, I have 1 for the magnitude in the x direction, and then for my bx component, I have 2, right? Equals 2. And then for my ay component, so right here, ay, I have 2. And then for, or maybe I'll make it a different number so that it's easier to follow the math if someone's not watching this. I'll make this 4, okay? So ay is equal to 4, and then by is equal to 3. So what does that look like? 1 plus 2, right, in the x hat, plus 4 plus 3 in the y hat. And when I add them together and I have my resulting vector, I'm going to leave these as 2 numbers and leave their directions. So I would have 3x hat, right, plus 7y hat. And that tells me that I have a vector where I'm going to go 1, 2, 3 over and 1, 2, 3, 4, 5, 6, 7 up, right, because I have positive x and positive y. So my resulting vector would look something like this. So this is my vector C. Okay? So hopefully that kind of helps make things make sense if you struggled with this in the beginning. Okay, so subtracting vectors, what do? So similar approach here. What I'm going to do is group the components. So I'm going to use the same example vectors for A and B. So I'm going to combine my AX and my BX. So I have 1. So the reason why I'm taking A first and then subtracting B is because A is coming before B, so A minus B, so AX minus BX, okay? So when I subtract them, it's just subtracting all of the components. So A sub x is the magnitude, so how much in the x direction. Okay, so in that case we have 1. B of x is 2, right? X hat, plus, so A sub y, we have 4, y direction minus B sub y is 3, okay? So that's equal to our vector D. So D is equal to -1 in the x hat, plus 1 in the y hat. So if I drew that on my coordinate system, okay, let me draw that a little better. Then on my coordinate system, okay, I would have -1, right, if this is x and this is y. So -1, and then I would have 1. Okay, so this would be my resulting vector in D if I drew it. Okay, so hopefully these are making sense. Again, if you kind of thought about it this way as like a point, you could also write your vector this way. This notation is okay as well. Okay, so hopefully so far so good. All right, so visualizing vector addition and subtraction. So essentially, this kind of helps us just understand what's going on. If I think about my vectors as if I'm telling somebody to go like, let's go 3 miles, you know, like to the east, and then 2 miles north, right? And then 1 mile, okay? Well, we'll just do 2. 3 miles east and then 1 mile north, okay? 3 east, 1 north. My resulting, the way that I would end up getting there, if you think about the vector as just kind of the shortest point between these two added together, this would be my resulting vector. Okay, so that would be like my direction to get there. When we're adding vectors together, if we kind of think about it in that way, I'm going this far in this direction, and then I'm going this far in this direction. So what's my resulting vector? It's going to go tail, right? Tail to head. So this is the resulting vector. So if for A minus B, it's essentially just reversing the rule here. So our D here, so I have A, right? And then if I think about it as you just start flipping it around. So you A, B, you can actually do it by flipping this B here. So I have A, B, and then I end up with C. So in this case, my D, I have my A minus B. Actually, this one I think will make a little more sense lower down. Okay, so for this one, I know that D is equal to A minus B, and then it's basically A plus negative B. So if this is the direction that B was going in the first place, right, and I just took and I subtracted my B, and then in this case, you see this A vector, I'm kind of moving it over, okay, and then the D is the shortest point from the tail of the first to kind of the head of the second, okay? So the same thing is happening up here. If these don't make sense to you, that's fine. I don't know if we're going to use them very much in this class, but kind of something to be aware of. People also look at the parallelogram rule, kind of when adding them. So if I have B and A, if I basically just think of like two parallel B vectors and then two parallel A vectors, so A, and then the vector that goes kind of in between them, that's maybe helps people visualize it a little bit more. This is just sort of to help you kind of understand what's going on with vector addition. Okay. So if you do have a subtraction, if you're subtracting the vector,